holiday weekend. Back into it here. All right, so we have some homework to do today. Please put it in Gopi's mailbox with all the TA mailboxes. Find it under this wonderful name. You have to learn how to pronounce it before you can pass the class. I'm still working on it. There will be another problem set appearing a little bit later on the web today. I'll let you know when it's available for download. And because we didn't have office hours this week, I'll have special office hours today at 1 o'clock in my office. If you have any final questions and you want to discuss with me. And we'll set up a weekly office hour with Gopi on Tuesdays as well. All right. Okie dokie. So let's see. So last time we were talking about the important problem of looking for eigenvectors and eigenvalues of operators. So eigenvectors, that's the German for characteristic vector, are characteristics of the map. So they are vectors that are mapped back to themselves up to an overall scale factor. And that scale factor is called the eigenvalue. And we are ignoring the trivial case, the null vector, that is the vector of all zeros, is trivially always an eigenvector of that. So we're not including those in our class of eigenvectors. Really what we're talking about are classes of vectors raised in the Hilbert space, because if we rescale the eigenvector by any scalar factor, that's also an eigenvector with the same eigenvalue. Okay, so the eigenvectors are different if they're not related to one another by just a scale factor. Okay, and so we stated, though we didn't prove, an important mathematical theorem known as the spectral theorem. The set of eigenvalues of a matrix is often known as the spectrum of the operator, for reasons that we'll remind ourselves of relationship to Fourier transforms. And the spectral theorem says that if the operator is a normal operator, meaning that it commutes with its adjoint, and examples of such operators are unitary operators or Hermitian operators, then there exists an orthonormal basis of the Hilbert space that are all eigenvectors of the normal matrix. Okay? So, if we were looking for how to actually find the eigenvectors and eigenvalues, what we remind ourselves what we do is solving this equation is equivalent to solving this equation. And that is to say, the set of eigenvalues are the roots of this polynomial. Okay? Right now, as I say, we're restricting ourselves to finite dimensional Hilbert spaces. We'll very soon, or soon enough, get to the important case of infinite dimensions and some of the challenges and subtleties associated with that. But for the moment, if we restrict ourselves to finite dimensions, then these are matrices, and this is just a determinant of this matrix is a polynomial of order d, and it has d roots, and those d roots are the d eigenvalues. And then to find the eigenvector, we plug that back in and find the vector that solves that equation. Okay? process of finding the eigenvalues of an operator, as you know, is often called diagonalization. So it's in a jargon. For the following reasons. That we know, so if we have a normal operator, then we said that the set of eigenvectors is an orthonormal basis. Of course, as we said, generally we have to normalize them if we want them to be normal, okay? I mean, normalized. So what that means is that, so since there exists a set of eigenvectors, according to this theorem, that are orthonormal basis, they form a resolution of the identity. So the set of eigenvectors forms a resolution of the identity by the spectral theorem. And because of that, that means that if I write a representation of the operator in the basis of its own eigenvectors, so we do that by inserting a complete set on each side, a resolution of the identity. So I have a sum over two dummy indices here. So I just inserted those complete sets. And this is an eigenvector. So this is equal to lambda times the eigenvector. And so this is equal to sum over lambda and lambda prime. I guess this is lambda prime, pardon me. Right? And since these were orthonormal, the inner product between two of these is 0 if lambda doesn't equal lambda prime, and 1 if the two indices are equal. And so we can sum over that and replace all lambda prime by lambda and write the familiar representation of the operator in the basis of its own eigenvectors as something which is, as a matrix, is with zeros everywhere else. So this matrix is a diagonal matrix. So represented in the basis corresponding to its own eigenvectors, the operator is a diagonal matrix where the diagonal entries are the eigenvalues. Okay? All right. So let's remind ourselves, let's prove some things about the nature of the eigenvalues. So let's suppose we're looking at a unitary operator. A unitary operator is a normal operator and thus can be diagonalized and has for its eigenvalues and eigenvectors. So let's look at some particular eigenvector. If I look now at the adjoint of this, so that becomes the bra U dagger around the star. Okay, so I just took the adjoint of this vector. If I now look at the inner product between those two vectors, that's equal to this times this is the magnitude of lambda star. And this, of course, is the identity. So what that tells me is that for a unitary operator, the magnitude squared of the eigenvalue is 1. Okay? So for a unitary operator, we can say that the eigenvalues are unit length complex numbers. It's a unit magnitude complex numbers, therefore they are on the complex circle, the unit circle. So that means that for a unitary operator, all of its eigenvalues are of this form. Okay? So unitary operators have eigenvalues that are phases. Okay? If it's a unitary operator. And as I said, you should think about unitary operators kind of like that. They're like the operator equivalent of phases. That's one reason to think about them that way. What about Hermitian operators? That's another example of a normal operator. Okay? So let's say I have a Hermitian operator, call it A. This is the eigenvalue. And I'm going to we switch around notation sort of a little bit willy-nilly here. Sometimes we denote the ket by just what its eigenvalue is, okay? I mean, you're familiar with that. For example, in the harmonic oscillator, you'll write the ket as n, right, for the number state. So sometimes we'll write u sub n, or sometimes we'll just write n and understand that that is a label for the particular eigenvector. So this is a Hermitian operator, meaning that it is self-adjoint.
Why is that eigenvalue?
No. I'm saying the eigenvalue here denotes which eigenvector. This whole thing is the eigenvector. I'm sorry if I'm confusing you. What I'm trying to say is that the notation that we often use is to denote the eigenvector by just saying it's the one with this particular eigenvalue. So, right. So if there, let's consider the following inner product. So this is equal to A times that, right? And if it's normalized, that's A, that's fine. Now let's take the complex conjugate of this. That's A star. But the conjugate of this matrix is, I take the adjoint of that and the adjoint of that, right? But this is self-adjoint. That is, say, it's Hermitian. So this is equal to A. So for a Hermitian operator, the eigenvalue is equal to its complex conjugate. In other words, it's real. So the eigenvalues of Hermitian operators are real numbers. Okay. All right. Yeah. All right. So, what else do I want to say here? Oh, yeah. So what I can say is that the eigenvectors associated with different eigenvalues of a Hermitian operator must be orthogonal. So, how do we show that to be true? Well, let's consider now, instead of this inner product, let's take this inner product where A and A prime are different eigenvalues. Okay? So let's consider that. Now this is an eigenvector, so this is equal to the action of this operator on this eigenvector is to replace it by an eigenvalue, right? So that's not true. That is true. Yeah.
I'm sorry, did you say A was equal to A prime or A is not equal to A prime?
Sorry, I meant not equal to, but wrote equal to. Okay? Sorry. Thanks. Okay, so that's true. What about the action? Now, this is something to be careful about. What is the action of A acting to the left on the K? Generally, to find that, the way to see how an operator acts on a bra is by first seeing what its action is by the adjoint, right? Because then, when I adjoint that, I get that. So the action of this operator on the bra is what I get by first acting its adjoint on the ket and then adjointing the whole thing. Okay, because I only know how things in some sense first. Okay. Now this is self-adjoint, so this is the same thing as this. Okay. But this is equal to this. This is a real number because we said that the eigenvectors of a Hermitian operator have real eigenvalues. So this is then equal to this with that because I don't have to start. So for a Hermitian operator, if I have an eigenvector on the right and on the left, it's the same action. Okay, so that means that I can equally well act this to the left, and I get A prime. Because it's Hermitian. If it weren't Hermitian, this would be A star, if they were unitary. right? Okay, so that tells me that A minus A prime times this inner product is 0. If I just subtract this from both sides of the equation. And since I assumed that these were eigenvectors with different eigenvalues, that is to say, they are non-degenerate. That's how we call eigenvectors associated with different eigenvectors associated with different eigenvalues are called non-degenerate. So since this doesn't equal this, it must mean that this is 0. Voila. Everyone loves writing QED. So, if we have non-degenerate eigenvectors, as to say we have different if the different eigenvectors don't have the same eigenvalue, they have different eigenvalues, then they must be orthogonal. Okay? All right. Now, what about the case of degeneracies? What do I mean by that? Well, let's just talk about things. Let me just try to stay a little bit consistent with the notation. I know it's just yeah, things are kind of around here, but that's okay. Okay, so I'll just say this more generally. So let's suppose there is a set of eigenvectors that I'm going to note as follows. U is sub lambda superscript I, okay? Where I is an index that goes from 1 to up to some number g for that particular lambda. So it has that many elements. This g is called the degeneracy. What do I mean by degeneracy? Well, what I mean is that for every one of the vectors in this set, it has the same eigenvalue. So this set of vectors, these are called degenerate eigenvectors. These are eigenvectors that are different, meaning that they're not parallel to one another, because when I'm talking about different eigenvectors, they can't just be rescaled by a constant. So they're a linearly independent set, but nonetheless, they all have the same eigenvalue. Such sets are sets of degenerate eigenvectors. Okay? All right. Well, what can I say about such a set? Well, first of all, it's not guaranteed that eigenvectors that are within this set are orthogonal to one another. It's not guaranteed, because say these ones are Hermitian operator, because this proof relied on this assumption. It's perfectly possible that this could be 0 just because the eigenvalues are the same, but this doesn't have to be orthogonal. Okay? So, what that means is that the following is true. The set of degenerate eigenvectors are linearly independent. They're different eigenvectors. They're not parallel to one another, which means that if I take any superposition of them with some coefficients, this vector, let me call it D, is also an eigenvector of N. Is that clear? How do we know that? How do we know that this guy is an eigenvector of M with the same eigenvalue? Well, we could just check it quickly, right? If I act this operator on this superposition, well, every one of the members of the degenerate set is also an eigenvector, and I can factor out that lambda and get back the same superposition, because that lambda is the same for all members of the sum, and thus can be factored outside of the sum. So that says I can, every superposition of vectors within this space is also an eigenvector with the same eigenvalue. So what that says is that this set spans a subspace of the Hilbert space, which we will call such that this is an eigenvector for all vectors in this subspace. Okay? What that further means is that we can, since this is a subspace, we can pick an orthonormal basis for that subspace, right? Every vector space in our Hilbert space, that's a Hilbert space, there exists orthonormal bases. We don't have to pick arbitrary bases. Means there exists a set of vectors the dimension of this Hilbert space is the degeneracy. So there exists a set of vectors which form an orthonormal basis. That is to say, any two of them are orthogonal. And we can normalize it. So, this, of course, goes back to the spectral theorem, the existence of this orthonormal bases. There always exists orthonormal bases which diagonalize the whole matrix. Okay? And so, what can we say about this? Well, what this says is that we can decompose the Hilbert space into a set of subspaces. Okay? So that's just to say, for a Hermitian operator, the total Hilbert space decomposes into a Hilbert space associated with each eigenvalue of A. So there is, say, A1, A2, dot, dot, dot. This symbol here is what we call the direct sum. Each one of these Hilbert spaces is a subspace of the total Hilbert space.
What's the backwards E mean?
There exists. So this is for all. And this symbol means there exists. Okay, so the set of A are the eigenvalues. And each A has a degeneracy G sub A. Okay, so the dimension of this Hilbert space is the degeneracy. Now that degeneracy might be 1. That is to say, there's only one eigenvector associated with that eigenvalue, in which case each one of these would be a one-dimensional Hilbert space, in which case there would be D such one-dimensional Hilbert spaces associated with the D distinct eigenvalues of a D-dimensional Hilbert space. Or it might be the case that this guy's one-dimensional, this guy's three-dimensional, this guy's one-dimensional. They can all be different degeneracies. There's no rule here about that. Okay? Now, what does this mean, direct sum? What this means is that this subspace is orthogonal to this subspace. That's to say, every vector in this space is orthogonal to all the vectors in this space. What's examples of this that we're more familiar with instead of using this example? Suppose I have three-dimensional space. Here we are. This space is a direct sum of the vectors along the z-axis with the vectors in the xy plane. Okay. So here's the xy plane. Here's the z-axis. Any vector in three-dimensional space is a direct sum of a vector along the z-axis and a vector in the plane. Okay? So this is a subspace, a two-dimensional subspace of three-dimensional space. This is a one-dimensional subspace. Okay? this is, could we think of as a union of the sets, but it has this other structure on it with inner products and such. Okay? All right, so how do we know that this is true? That these Hilbert spaces are orthogonal? Any guesses, any ideas, any notions? Yeah.
The eigenvector proof.
Yeah, so exactly. We just proved that if we have two vectors, which are eigenvectors of the Hermitian operator, associated with different eigenvalues, then they must be orthogonal. And that's what's here. Everything in here is an eigenvector of the observable A with this eigenvalue, bless you, and everything in this subspace is an eigenvector of this observable with that eigenvalue, but these two are different eigenvalues. And by the proof over here, they must be orthogonal. So what we can say is generally, we have a basis for the total Hilbert space, which I'll denote E sub A I, where A, you have A1 up to whatever the nth eigenvalue is, and then I goes from 1 up to the particular degeneracy. Okay? So what we can say is that two eigenvectors I should say orthonormal. Let's say there exists an orthonormal basis such that if they're associated with different eigenvalues, they're orthogonal, or if they're for the same eigenvalue, but there can be different vectors within one of these subspaces, we can always choose them to be orthogonal. And what that tells me, since this is a basis, I can write a resolution of the identity. That's to say the total Hilbert space for the system, I sum over all the possible eigenvalues up to the nth eigenvalue. And then for each one, I have to sum over all the degenerate eigenvectors within that. Sum over all the vectors. That is a way of writing a resolution of identity. This operator, summing over all the eigenvectors in this outer product for a given eigenvalue, is what I'm going to call a projection operator onto the space associated with eigenvalue A. So this is projection operator onto the subspace H sub A. Why is that a projection operator onto that space? Well, let's look back at this example. This is this simple picture here. Here's some arbitrary position vector in three-dimensional space. Suppose I wanted to project this operator onto the xy plane. Okay, so this is when I call R in the xy plane, that vector. how do I obtain this vector? Well, I mean, that vector is the x-coordinate of that and the y-coordinate of that. That's what that vector is. The z-coordinate is that vector. Okay? And what are these? Well, to get this, I have to project this onto I'll put the ex on this side plus dy dot r. Remember, I can write this with this on the other side because it's just a number, it doesn't make a difference. And this, we recognize as a dyadic that we did in the first lecture. This is a projection operator that projects me into the xy plane. Or if I want to put the double arrow on it. So the sum of these outer products is a projection onto a subspace. That subspace in this case was the xy plane. The subspace here is generally the subspace associated with the span of the eigenvectors that all have eigenvalue A. And the dimensionality of that subspace depends on the degeneracy. If there is no degeneracy, if all of them have degeneracy 1, well then there's no sum to do, and this is a more familiar expression. Okay. So we can resolve the identity as a sum of projectors onto orthogonal subspaces. The most fine-grained resolution would be a projection onto the z-axis, the x-axis, and the y-axis. So, what I can say then is that in this orthonormal basis, the diagonal representation of the observable, of the operator, we'll talk about that soon. A is, well, let's just for fun say this is A1. So here's a matrix. It's a diagonal matrix. It's got zeros everywhere that I didn't write a number. But I've written in terms of blocks. Okay? So this is the block associated with the subspace associated with the eigenvalue A1. It's a one-dimensional subspace because this is a non-degenerate eigenvalue. Then I said that this eigenvalue was fourfold degenerate. Maybe it is. In that case, this block is all of this is a 4D block. That's to say the degeneracy of that eigenvalue is 4. And then there's a block associated with H3. This is a 3D block, just because there's nothing special about 3 and 3, it's by chance. Okay? Oh no, that's 2D. It looks like, I guess, now it's 2-dimensional. All right? Okay. So one of the things that one has to be careful about when one is diagonalizing a matrix is that if you have degenerate eigenvalues, you're not guaranteed that the eigenvectors are orthogonal. So doing the thing with the characteristic polynomial and plugging it in, you won't necessarily, just by doing that, find orthogonal eigenvectors. If not, after the fact, you have to take the subspace of eigenvectors, the linearly independent case, and orthogonalize them by something like the Gram-Schmidt orthogonalization procedure. Okay? Okie doke. Now, the last topic that I want to cover in this mathematical foundations is the question about compatible observables. Is it able or able? Thank you. It's embarrassing saying the whole course spelling, but true. Compatible observables, or compatible operators, and mutual sets of eigenvectors. So, let us suppose that we have another Hermitian operator. Suppose that A and B are Hermitian. And B and A commute. Remember, the commutation is the operator you get by multiplying them together and then subtracting them in the other order. Okay. So, let's just suppose that's true. And let little a be an eigenvector of the operator A hat. Then the vector that I obtain by operating B on that is an eigenvector. With the same eigenvalue. That is to say, if I look at the action of A on this vector, I claim that that's equal to this. Is that obvious? Sure, it's obvious because they commute. Because they commute, that means A times B is equal to B times A. And since this is an eigenvector with eigenvalue, this is an eigenvalue of A by assumption, that's equal to this. Yay, once again, trivially true. Okay, notice where did you go hiding there?
There.
Oh yeah, ran away. Thank you. All right. So, now, if it is the case that this vector is non-degenerate, okay? that means what? Well, that means that this vector must be proportional to A. Because, as we said, eigenvectors are really a class of vectors. They're arrays in Hilbert space. And all things with this along the same ray are the same eigenvector. And that's all that's possible because this is non-degenerate. Okay? That means that B on A is some number, which I'll call little b, on A. That is to say, this vector is really denoted by two indices. That is to say, this vector is also an eigenvector of B. So if we have two operators that commute, and if we have a vector which is an eigenvector of one of those operators, it must also be an eigenvector of the other operator. It doesn't have to have the same eigenvalue. It can have a different eigenvalue. But it must be. And so typically we would denote both eigenvalues in the ket. Okay. Right. Now, what can we say if A is one of a degenerate set of eigenvectors of A? Well, then what we know for sure is that B on this vector is an eigenvector of the operator A hat, capital A hat. But we can't say anything more than that. Because here, because it was non-degenerate, that insisted that that was true. But if it's degenerate, we can't make that conclusion. And thus, what we can say for sure is that this thing is a member of this subspace. That's what we can say. It maps the eigenvector little a somewhere within that space. Because every vector in this space with that eigenvalue, with that index, is an eigenvector of A hat. And that's what we proved. Okay? What that means is that given another eigenvector, A prime, where A prime is not degenerate with A, what can I say about this matrix element? This is in this space. This is not. What can we say this matrix element is, therefore? Zero. It has to be. Because we said that eigenvectors in subspaces associated with different eigenvalues are orthogonal. Therefore, this, whatever this vector is, it's got to be orthogonal to that. Okay, so that means that if I have a, so suppose that I have, so let this set of vectors be an orthonormal basis of eigenvectors of A and A and B commute. Then, what can I say for sure, based on what we've said, about the matrix representation of the operator B? Well, what I can say is that B is block diagonal. So if I look at that, let's just take that as the example. What the B will look like is there'll be a B1, there'll be a B2, which is this is a 1 by 1. This is a what did that one was? 4 by 4. There'll be a B3. It's a 2 by 2, etc. I can't say a priori that these are diagonal matrices. They're just 4 by 4 matrices, some 4 by 4 matrix. This one is, of course, just a number. And this is some 2 by 2 matrix. But all the off-diagonal elements between different blocks are necessarily 0 because of this. So we have what we call block diagonalized B. We haven't fully diagonalized it yet. Okay, so another way of looking at this is the following. Because we have this basis, we said that there is a resolution of the identity in terms of a sum over all projections onto the different spaces, subspaces, associated with the different eigenvalues of A. That's what we wrote over there. Let me just, I forgot to write one definition of the, or one property of projection operators. So this is a projection operator onto the space HA. And those projection operators satisfy the following property. If the two spaces, subspaces are different, then that projection is 0, right? Because they're orthogonal. However, what happens when A equals A prime? That's projection, projection again. But if I project it at once, it doesn't do anything different. So projection operator squared is itself. Okay? So let's look at B, the operator B, in this space. I'm sorry, yeah, in this representation. Well, that is the sum over A prime, projection A, B, however, because of this, if these are different projection on different spaces, the off-diagonal matrix elements are all 0. So the only non-zero ones are when they're the same. So I'll call this BA, where BA is equal to the projection onto that space. Okay? And that's equal to the sum I and I prime E A I E A I B E A I prime so these are the matrix elements of these blocks. Those matrix elements need not be diagonal in general. Yeah?
Why did you go from sum over 2 variables to sum over 1?
Yeah, good point. So that followed from this. In other words, we said that when B commuted with A, it must be true that there are no off-diagonal elements of B between vectors associated with different eigenvalues. Okay, however, although it's the case that these matrices need not be diagonal, they are Hermitian matrices. Okay? So I was considering A and B to be 2 Hermitian operators. This is a Hermitian matrix. It's a 4x4 matrix. And therefore, we can diagonalize it. Right? In which case, this will be, we can always find a set of orthonormal vectors okay? So, the operators BA, that is the operators projected into the eigensubspaces of A, are Hermitian. Implies we can diagonalize them. Okay. Now, as we said, so if the eigenvalues of BA are non-degenerate, then automatically they are orthogonal. And we have found a mutual set of eigenvectors that are orthonormal that simultaneously diagonalize the operators A and B. However, maybe there are degeneracies in these eigenvalues. So we diagonalize these blocks, but now some of these blocks have subblocks in which there are degeneracies. Okay, and within those degenerate spaces of these guys, it may be the case that two eigenvectors, they don't have to be orthogonal. Of course, we can always orthogonalize them, but they don't automatically have to be orthogonal. So, what we have here then is that, so if the eigenvalues of BA are degenerate, they aren't guaranteed to be orthogonal. So what that means is, suppose there is a third operator. And let C also commute with A and B. And A and B commute with one another. So we have these new sets of eigenvectors with degeneracy. Well, let me have E, A, I. Ugh, I don't want to say this. I have A and B. There's degeneracy of A and degeneracy of B. Each one of these could be degenerate. Then the matrix C, well, it has a certain block diagonal structure, right? So I can look at this now. There's C, let's say this was C11, one dimensional here. This is, then I have C, let's say this guy was the first eigenvalue for B. So this was 4-dimensional, but for B it's 1-dimensional. This is C for 2. And C for 1. Let me explain what I'm trying to say here with all this notation. So let's just, for the heck of it, say that when we diagonalize this matrix, this guy was a 1-by-1. There was one eigenvalue that was non-degenerate. There was a second eigenvalue that was doubly degenerate, and then there was another guy that was non-degenerate. When I express C in this basis, it is block diagonal. This guy is going to be a 2-by-2 matrix. And I just keep going. And that leads us to the final result. Which says the following. a so-called mutually, or a complete set of mutually commuting Hermitian operators let's say A, B, C, or however many there are, such that every one of these guys commutes with everybody else in the set. Completely specify a vector in Hilbert space. What do I mean by that? The normalization in phase. That is to say, if there are a set of operators, Hermitian operators, such that these are mutually eigenvectors. Specifying, if I don't have the complete set of such operators, specifying it as just an eigenvector of one of those observables does not uniquely specify the state in Hilbert space, or the vector in Hilbert space. Let's just make this more physical for a moment, just to remind you of something that you know. Come back to. Angular momentum. So suppose I look at the angular momentum operator. L, position across momentum. Now, if I look at the magnitude squared of that vector, I can look at the eigenvectors of that operator. But, so for example, we know, if this is orbital angular momentum, that there are eigenvectors of this where L could be 0, 1, 2, 3, etc. However, specifying the vector as an eigenvector of L squared does not tell me uniquely what vector I'm talking about, because there is degeneracy. We know for a given L, the degeneracy is 2L plus 1. There are 2L plus 1 different vectors in Hilbert space, which all have the same eigenvalue of L squared. However, I can completely specify what vector I'm talking about by specifying another operator, not just L squared, but another one that commutes with L squared. In fact, a complete set of mutually commuting operators in this case complete set of mutually commuting operators, is the standard set elsewhere and the projection along the z-axis.
Yeah, that would fit any type of momentum, right? And like spin.
Yes, any type of angular momentum, whether it be orbital or spin indeed. And in that case, we specify the eigenvectors of this are, well, so now we have two eigenvalues, L and M, where this and this is this, where N goes from minus L to L in integer units. Okay. So this is an example of a mutually commuting set of observables which are have a simultaneous set of eigenvectors, and I need to specify all these eigenvalues in order to uniquely specify the state. So this will have important physical implications that we'll get to soon. All right, we'll stop there. And we're done now with all the sort of basic mathematical formalism we need.
So much strong.
Yes, indeed.